How do we go about solving this integral? Unless you're quite used to these kind of integrals, this is pretty hard because it's hard to come up with a substitution for these integrals. Though if you try hard enough, you'll be able to find a good substitution. But we aren't doing that today. In this equation, we are solving this more brilliantly. Consider the function inside the first integral. Now, for the sake of simplicity, let's label this as y. So, if we solve for x, we will get the inverse function. And as you can see, we've got that the inverse function is the square root of 2 to the y minus 4, which is just what we've got inside the second integral. Now look at what the values of the function log base 2 of x squared plus 4 are when evaluated at the limits of integration. So, did you notice? They are the corresponding limits of integration of the second integral. So we are good to go and use this formula. We already checked for whether the limits of integration were corresponding to one another and that both integrands are inverses of one another. So we can perfectly use this without any problem in order to get 8 square root of 3. Well, we were able to solve that integral, but the question we have yet to address is, why does it work? Consider the integral of the inverse of f of y going from f of a to f of b. Now apply the substitution y is equal to f of x. When you plug this all into the original integral, and since we are doing the composition of the inverse with the function itself, we'll get the integral of x times f prime of x dx from a to b. Since we've got a product in the integral, we are going to do integration by parts, thus getting this expression right here. Recall that the integral from a to b of x f prime of x dx is equal to the integral from f of a to f of b of the inverse of f of y dy. Rearrange the expression and voila! This is Laisant's theorem. We aren't done yet. If you're more of the visual kind, let me tell you, pal. This is your lucky day. Consider a function of any shape, it doesn't really matter what it looks like. Now let's draw the rectangles made up by f of b and b and f of a and a. If you remove the blue area from the pink one, you'll get an L-shaped figure whose area will be the difference of the areas, that is, b times f of b minus a times f of a. Now remember that the integral geometrically represents the area under a curve, so the area under the curve traced by f of x from a to b is nothing but the integral from a to b. And if we want to know the area between the y-axis and the curve ranging from f of a to f of b, we've got to integrate the inverse function from f of a to f of b along the y-axis. And the area of this L-shaped figure is the sum of the integrals. Now observe both graphs. We can compare them side to side and conclude that they are the same.